All right, good morning, ladies and gentlemen. This is Mr. Young. As you've probably figured out by now, I'm not here today. Sick kid, sick Mr. Young. Everybody at my house is sick. Life is fun. So, with that, we're going to try and truck forward because, unfortunately, we don't have a ton of time to just take a day off. So, we are going to cover this 5-7 section as best we can via video. And God willing, I'll be back tomorrow to help fill in any gaps that the video leaves. You should have in front of you this Algebra 2 note sheet for section 5.7. Typically, I'd have a full PowerPoint ready, but because of the short notice of the illness, I haven't been able to put together all those materials, so we're just going to work directly through this worksheet. So there might be some awkward pauses as you have to watch me type, that sort of thing. We'll try and make this go as smoothly as possible. And again, take notes, write down questions that you have, like specific things that you don't understand. That way, when I get back in tomorrow, we can quickly and easily fill in those gaps and get you guys where you need to be so that we can get you done what you need to get done. All right. Thanks, God. Thanks a lot for your patience in this, and let's get into it. The first thing we have is just some vocabulary, and we basically already talked about this. It's the idea that a zero, a root, a solution, an x-intercept, those all mean the exact same thing. That's what I mean by the four statements are equivalent. If I say that C is a zero, if I say C is a solution, if it's a root, if it's an x-intercept, those all basically mean the same thing. And then number 3 here is just saying that if x minus c is a factor, basically c is also a solution. So you're kind of adding factor into that. And we'll be able to use these terms more or less interchangeably as things go on. This section deals with what's called the fundamental theorem of algebra. Take a minute, let that sink in. Fundamental theorem of algebra basically is that if you have a polynomial with a degree of n, then it has exactly n roots. So if we look real quick over here, this is a cube function, and you'll see that we have one root, one solution that's real, but it's a cubed polynomial, third degree polynomial. So therefore, if we have the one real root, we have to have two imaginary roots that occur somewhere around here in this area. That's the meat of this section, is just understanding that. However high the degree is, that's how many roots there are. And if we can find one real root, then there's, in this case, two imaginary roots remaining. It's going to be an issue of finding all the real roots and then also finding all the imaginary roots for polynomial functions. Okay, so let's start with a basic, just finding the zeros based off of the graph. And we've got the steps that you're going to follow listed out here. So first, graph and find the rational zeros. Those are the real ones, the easy ones to find. And I'm going to be using Desmos just because I'm working off of a computer. You guys should practice working with the calculators. Desmos does make it really easy. For example, I've typed in f of x equals x cubed minus x squared plus 2x plus oh no, there it is, plus 4, there we go. And all I have to do is really click on the root, and then it shows me, oh yeah, one of my solutions is -1. If you're using the calculator, you have to do the second calc 0 function. It'll show it up really nice, but if it's a nice whole number like this or an integer, we can just go to the table as well to find these out, and that's listed in the notes. Use the table to use the 0 command. Whatever you got to do to find these easy zeros. So there's my first one. Then once I've got that, I have to use synthetic division to try and break this down to a quadratic. So I know that -1 is one of my roots. So that means then if I do synthetic division, where, you know, if I'm over here and I get my little box, I'm going to expand this real quick. I basically am going to, you know, do my synthetic division with my factor of -1, get my depressed polynomial that we talked about yesterday, and I'll have, you know, go through all the work. Should look like this. This then comes out to x squared minus 2x plus 4. So then ultimately what I'm allowed to do is rewrite this now as, you know, factored as x minus 1. Oops, excuse me, that should be x plus 1, because the factor itself is -1. So x plus 1 times x squared minus 2x plus 4. Then from there, I now look at x squared minus 2x plus 4. That's my quadratic, and I'll use that to get my second two solutions. Remember, if I set x plus 1 equal to 0, that will give me my first solution, x equals -1, which we got from the graph. Then I have my second factor, which is this x squared minus 2x plus 4. That will give me my second factor, or excuse me, my second factor. And because it's a quadratic, I'm expecting to get two roots from that, two more solutions from that. And if I look back at the graph, because I can tell my original only had the one real root, which I got from this factor, I'm expecting to get two imaginary roots from this. Now, yesterday I misspoke, or at least we'll say that I've changed my mind since then, but I am going to require exact answers for these that come out in imaginary form. So you are going to need to use the quadratic formula by hand to get these exact roots. C quad 4, as wonderful as it is, gives decimal approximations, and just for the simple fact that they're not super useful, I'm going to go ahead and require that you guys do that by hand and get those exact solutions. So if that makes you dislike me, I'm sorry. I'll give you a hug later if you need one. Otherwise, we will get through this together. So what I would do, negative b plus or minus the square root of b squared minus 4ac all over 2a. You can look that up anywhere on the internet if you don't have that memorized. And then you'll plug in, 1 for a, -2 for b, 4 for c, and you'll get your roots. Now, again, due to time constraints and technology constraints, I'm not going to show that right now. But ultimately, what you should get is x equals -1, which we get from this first root here, or first factor here, excuse me. And then again, after you use quadratic formula by hand, you should be able to get, 1 plus or minus I square root of 3. Now, again, my presumption is that you guys have done this in chapter 4. If this part here, getting that imaginary root, is still a real challenge for you, do me a favor and at least get to this point, okay? At least get to the point where you've got it factored and you understand that this factor is going to give us the two imaginary roots, which we know exist from looking at the graph and that fundamental theorem of algebra. If we can at least get to here, and then tomorrow once I get back, pray to God, we'll be able to then practice getting these imaginary answers down, okay? All right, for the next chunk of the video, and if at any point you guys need this paused, just please ask politely that the video be paused and copy anything you need to get copied down. But for the next part, I'm going to come back over here to Desmos, and what I've done here now is I've adjusted this second example, example B, so that you can see the full screen here. And for sake of time, I won't make you guys pull this out in your calculators, but I will highlight here's one of the roots at 0.50, so in other words, one of our roots occurs at 1/2, and the second real root occurs at 5. Now again, with that fundamental theorem of algebra, I can tell that with a 4th degree polynomial, there's going to be exactly 4 roots. 2 of them, 1, 2, are real, they're rational, and then the third and fourth one are going to be the imaginary roots, which you can see where it kind of does this weird little wiggle thing right here around x equals 0. So what you need to do, and I would pause the video as you do this, do your synthetic division on 5, get it down to a cubic, then do synthetic division on what's left on the 1/2, and realize that with that 1/2 you're going to have to divide those coefficients by 2. I know, it's a lot. But then once you do that, you should be down to the quadratic that you can then plug into the quadratic formula to get your two imaginary roots, okay? Pause the video, take 5-10 minutes. Once everybody's kind of had a chance to take a shot at this, go ahead and unpause it. I'll have a solution there, and you guys can check what you did compared to what I did. Okay, so hopefully you were able to do your synthetic division. I started off by doing the synthetic division of 5. It's a little easier. And then once I did that, I got down to 2x cubed minus x squared plus 8x minus 4. Then from that, I did the synthetic division of 1/2, which is the second factor of 2x minus 1. And once I did that, I got down to x squared plus 0x plus 4, so just x squared plus 4. Once I've got these three factors, X equals 5 I already know from the graph, x equals 1/2 I know from the graph, and then this last factor, the x squared plus 4, that's the quadratic I'm looking for, and that gives me x is plus or minus 2i. Okay, so again, I know that I'm throwing a lot at you, but really what's new here is that we're looking at the graph. Okay, look at the graph, find the, however many real roots there are, and then from there use synthetic division with those two roots to get down to a quadratic, which we can then factor using the quadratic formula to get the remaining, usually two, imaginary solutions. All right, take a quick break, and then we're going to move on to the next chunk. That next chunk is simply identifying how many zeros there are. So we've kind of already talked about this. This Descartes' rule of signs is an old rule that we used to use to kind of guess, but now with graphing calculators, we don't have to guess anymore. So we're really just still using that fundamental theorem of algebra, which is we look at a graph and we count how many real zeros they are. We count how many of them are positive real and negative real, which is an important thing in certain contexts that hopefully we'll get to later. And then from there, whatever's left over from the total degree of the problem, that has to be imaginary. So if I take this first problem and I've clicked over here and I've now copied it over into Desmos, without doing anything fancy, I basically just need to look at the graph and I need to say, okay, how many times is across the x-axis on the negative side, how many times across the x-axis on the positive side, and then whatever's left over, that's how many imaginary roots I have. Now, it just so happens that with this example, as you can see, there aren't any real roots. This one has no real solutions. So for this one, we would just plug in 0 for the number, for 0 for positive and 0 for negative. And then since it's a 6th-degree polynomial, there has to be 6 imaginary solutions. Now for this example here, I'll copy this over as well. And that's now this orange one, which we'll zoom out a little bit to see here. Now this is a 5th-degree polynomial. And again, just by looking at it, we can tell, okay, there's one negative real root, which we can see here when it crosses the x-axis. And then all these ups and downs over here represent what's left over. Now if there's 5 total roots, one of them is real, that means there must be, wait for it, 4 imaginary roots. And so for a problem like this, you would just type in, or you would write in, because you'll be using your pencil, not a computer, you'll write in 0 positive, 1 negative, 4 imaginary. That should always add up to 5. So the second chunk of problems on the worksheet just deal with that. Now, before we move on to part 3, I am going to stop this video and start another one. I've got some limitations on this software that I'm using, so please click over to the next video and we'll continue and wrap up there as quickly as we can. Thank you.